Hi, everybody. Here is a solution to a problem requested on the forums. Section 5.1, exercise 8. It's got three parts, A, B, and C. I'm just going to prove parts A and B because part C asks to prove the same results for matrices, and the proofs are nearly identical. You just use matrices instead of the linear transformation T. So let's start with the first part, part A. Prove that a linear operator T on a finite dimensional vector space is invertible if and only if 0 is not an eigenvalue of T. So we'll prove part A. So we'll start with T. It's a linear operator, so that's a linear transformation from a vector space V to itself, where V is a finite dimensional vector space. And we want to prove that T is invertible if and only if 0 is not an eigenvalue of T. So let's observe what would happen if 0 were an eigenvalue of T. T has an eigenvalue of 0 if and only if, well, what is an eigenvalue? It's a scalar so that there is an eigenvector and the eigenvalue is associated with that eigenvector. So in other words, if and only if there exists a vector little v in V, the vector space, so that V is an eigenvector of T. In particular, that means that V is not the 0 vector. And when you apply the linear transformation T to the vector V, you get the eigenvalue times the original vector V. But if the eigenvalue is 0, that means that you're scaling the vector by 0, which then, of course, is the 0 vector. So in other words, T has an eigenvalue of 0 if and only if there is a vector that is not 0, but gets sent to 0 by T. Well, that, of course, is true if and only if there exists a V in the vector space, so that V is not the 0 vector, not the 0 vector, but V is in the null space of T, because that's what the null space is. It's a set of all vectors that get sent to the 0 vector by 0. So in particular, then, that means that the null space of T is not only the 0 vector. There's something else in there. And from another theorem that we already know, this is true if and only if T is not 1-to-1, otherwise known as injective, which then in particular is true if and only if T is not invertible, since T goes from the vector space V to itself. Not being 1-to-1 means that you are not invertible, and not being invertible means that you are not 1-to-1 and that you are not onto, because of the vector spaces involved. So this proof is bidirectional the entire way. So what we've actually proven is that T is invertible if and only if 0 is not an eigenvalue of T, because we've shown that if T is an eigenvalue of 0, well, that's actually true if and only if T is not invertible. All right, then let's proceed to part B. Part B asks, let T be an invertible linear operator. Prove that a scalar lambda is an eigenvalue of T if and only if lambda to the power -1 is an eigenvalue of the inverse of T. So let's suppose that lambda is an eigenvalue of T, linear operator, again from a vector space V back to itself. Then this means that there exists an eigenvector V in the vector space with V not the 0 vector, and t applied to v is the same vector, only scaled by that scalar lambda. Now, since t is invertible, we can apply t inverse to both sides of this equation. Well, on the left-hand side, t inverse of t should just leave us with the vector v. On the right, by linearity, we can pull out the scalar lambda. And now we have the inverse of t applied to the vector v. The lambda's on the wrong side, but of course we can now multiply on both sides by the multiplicative inverse. Lambda to the power -1. The only possible problem that might occur is if lambda were 0, but of course from the previous problem we know that t is invertible if and only if 0 is not an eigenvalue. So if we have an invertible linear transformation, then in particular lambda is not 0. So let's add that here as a note. By part A, lambda is not equal to 0. Therefore, this step is justified, and we can say that lambda inverse times v is equal to, well, lambda inverse times lambda is the multiplicative identity in the field, namely 1. So t inverse applied to v is just v, but scaled by, instead of lambda, the reciprocal of lambda, the multiplicative inverse of lambda. Right, so technically this is only one direction of the proof. If lambda is an eigenvalue of t, then lambda inverse is an eigenvalue of t to the -1. But actually, again, these steps are all invertible. If we started with lambda inverse as an eigenvalue for t inverse, as in this last step, then that would imply the previous line, which would imply the previous line, which would imply the previous line, which would imply, of course, then that lambda was an eigenvalue of t. So I could add an if and only if there, and an if and only if maybe here, and along each of these lines, every step is reversible. So we've in fact proven the if and only if conditions. So hopefully that's clear, makes sense, and is helpful to you guys.